Hello, my name is Amir Holtzman and I will talk about utilizing nanotechnology for thermoelectrics. So let's first talk about thermoelectric devices. These devices can do two things actually. They can convert a temperature difference into potential difference, meaning voltage, and they can also do the opposite thing, converting voltage into temperature difference. So there are two kinds of thermoelectric devices. The first kind is called power generators, and their action is based on the Seebeck effect. The Seebeck effect is known for around 200 years, and in this effect, when you have a material with free charge carriers, in this case it is a semiconductor of N-type, and once you apply a temperature gradient, usually by simply hitting one side, then the free charge carriers, in this case the electrons, they obtain energy from the heating, and they arise into higher energy levels. In these levels, which were previously unoccupied, in these levels the diffusion rate is higher. So you get actually a situation in which the diffusion rate of the free charge carriers from the hot side into the cold side the rate is higher than the diffusion rate of the electrons in the cold side to the hot side. So a long time you get a potential difference because electrons are leaving the hot side faster than they do leave the cold side. And so negative potential is developed in the cold side and a positive potential is developed in the hot side. And so this process continues until at a certain point an equilibrium is obtained in which the potential difference is large enough so that the electric field applied on the electrons is strong enough so it stops their movement. So at equilibrium you get certain voltage. You still have movement of electrons from the cold into the hot side and vice versa, but the net movement is zero. So at this equilibrium you get a certain voltage, and this is called the thermal voltage. So we started with a certain temperature difference, and we obtain voltage. This voltage can be utilized to drive current and perform electrical work. And the other kind of devices is thermoelectric coolers, and this is the effect that they are based on is the Peltier effect, also known for around 200 years. In this effect, you connect in series two conductors, again, materials with free charge carriers. It can be also semiconductors. So you connect in series two kind of conductors and you apply a voltage. So if we look at this circuit, for example, we can see that the electrons they start to move from the negative pole of the battery. They start to move in the iron, and in this movement they have some average energy. Okay, it depends on the Fermi energy of the iron, and once they get to the copper, since there is a difference between the Fermi energies of the copper and the iron. You can also call it a difference of the work function, it's the same idea. Once the electrons move from the iron to the copper, in this case, they have to gain energy. Okay, the Fermi level of the copper is higher, so they move into higher levels, which are in the copper. So doing that, they obtain energy from the environment, and thus the environment is cooled down. Okay, so now they move in the copper in an average energy which is higher, and once again they moved back into the iron. Again, now they fall in their average energy, and now they release energy into the environment, and now the environment is heated. So here we started with supplying voltage, and we obtained a temperature difference, okay, which can be utilized. This circuit can be utilized to perform active cooling. Okay, so in order to utilize and take these thermoelectric materials and make from them a thermoelectric device, usually you combine two materials, one N-type and one P-type, meaning semiconductors. You combine them to create a thermoelectric element, and from these elements you then combine many elements to create a thermoelectric device. So let's see how these elements are composed. If you look on the right, for example, for the power generation mode, you can see that the N-type and P-type thermoelectric semiconductors are connected in series. And by doing that, by combining these two materials, you gain two things. First of all, you can see we have here an electrical circuit. Okay, the N-type semiconductor conducts electrons, and the P-type conducts holes, meaning electrons in the valence band. And so the movement of electrons in the P-type and the N-type fits. Okay, you have an electrical circuit and the current is derived. Okay, so the two things that you gain once you have this kind of circuit is, first of all, since you connected two thermoelectric devices in series, each one of them, once you apply a temperature gradient, each of them, it creates its own voltage. So you combine these two voltages in series, so you gain a summation of the two voltages, okay? So you gain higher voltage. This is one thing. And the other thing is that you can notice that we have here an electrical circuit, okay? But if you take a look at the hot side and the cold side, they are connected only by materials with very low conductivity, thermal conductivity. Okay, these semiconductors, as will be explained later, have very low thermal conductivity. If I would connect them, the cold side and the hot side, by metal, let's say gold, since gold has very high thermal conductivity, I would diminish the initial thermal gradient. Okay, so the thermoelectric effect will diminish. Okay, so this special circuit enables me these two advantages, and same applies for the refrigeration mode, which appears on left. Okay, same idea also here. Okay, and next you simply combine many thermoelectric elements to create one big thermoelectric device. Okay, and you gain the summation of all the contributions of the elements. And this is how actually a commercial thermoelectric device looks like. Thermoelectric devices have several very important advantages. They are highly reliable. They're actually solid-state devices. They don't have almost any moving parts. They require a very low maintenance. And they are silent, they are clean power sources or active coolers, and they are compact, robust, and scalable. Now, despite these very important advantages, currently the usage of thermoelectric devices is quite limited. And the reason for that is that their efficiency is low when you compare them to other technologies. And so the current applications are very specific in applications in which these advantages are really critical. For example, when NASA sends a space vehicle that will go on for tens of years in space, and they won't be able to maintain it, they won't be able to solve problems, and so they use thermoelectric devices because of the very high reliability, etc. Some other applications are, for example, they are used in PCRs. They're used in cars, for example, to heat your seats and so on. And overall, the current market for thermoelectric devices is around tens of millions of dollars. Again, very small when you compared it to the overall potential. Okay, and again, this is due to the current low efficiency.